the concept of electric charge, which is interesting, and a very interesting law, which is Coulomb's law of interaction between electric charges. And that law is interesting because it is very much Newtonian-like again, apparently, up to some point. There are differences and similarities which you know most probably about, okay? But the yellow word which emerges out of this menu is the concept of field. That is the revolutionary and very interesting part of what truly electromagnetism has to say about these phenomena, about physics. I will emphasize this a lot because if you read Albert Einstein's texts on the evolution of physics, on how he came to think about his relativity theories and so forth, there is in these texts very often a quite strong emphasis on the concept of field. For Albert Einstein, the work of Michael Faraday especially, he admired particularly Michael Faraday's work. I'll speak about it. And of course James Clerk Maxwell's work, because these two physicists and thinkers, I would rather say thinkers, introduced for the first time in physics the concept of field. Okay? Why am I saying this? Because I just want to explain to you that the concept of field does not fit, as it is described in electromagnetism ultimately, does not really fit into the mechanistic Newtonian worldview. Right? It says something new about nature. Right, so there are several things which you can think about or speak about in electromagnetism, many of which you know. Gauss's theorem, the concept of electric field lines in general, the concept of electrostatic equilibrium of charged objects, charge conducting objects. And this is rather related to static electricity, but there is also a dynamical form of electricity, and that of course corresponds to electric, with the understanding and description of everything that has to do with moving electric charges, so dynamical electricity, that means electric currents, Ohm's law, condensators, capacitors, the capacitance, and all these electric circuits and constructions and so forth, and so forth, and so forth. So this is all about electric phenomena, I would say. And then you have three types of very important experiments that show something wonderful in essence, especially the experiment of Hans Christian Oersted, a Danish physicist, that shows something interesting. You can essentially produce a magnetic field without magnet, just with electric currents or something like that, yeah? And so forth. And Michael Faraday has devised or imagined another fundamental type of experiment which shows that the electric conducting, a conducting piece of wire, when placed in a magnetic field, it undergoes the action of a force of magnetic origin, a magnetic force. And another experiment of Adrien-Marie Ampère, a French physicist, confirms, in a sense, the two preceding experiments. And this is all showing that there is a relation between electricity and magnetism. Okay, electricity in some sense can produce, in some sense, a magnetic field. And we can speak also about the Lorentz force, the concept of Lorentz force, as a consequence of all that, I suppose. Rowland's experiment, Henry Rowland's experiment, which shows something interesting, and so forth. And then you can hardly see it, but maybe we should turn some light off or something, at least one, maybe. There is the, of course, important ingredient which is due to Thomson, Joseph Thomson, and the discovery of the electron and everything that has to do with that is important because the electron, explains conduction and what electron and what currents mean and what currents are in conducting materials, of course. That's the concept of electric current. Okay. Then we will speak about the electric field, and of course we will also mention the magnetic field and the flux of both fields through a surface, the concept of flux of the electric field and of the magnetic field, extremely important. And then you have further wonderful experiments of this person called Michael Faraday, okay, which shows electromagnetic induction. And this is the other part of the story. Right? A varying electric field somehow can produce a magnetic field, but somehow a varying magnetic flux or magnetic field can vice versa produce an electric field. So both concepts, both entities, right, the electric field and magnetic field, are not two distinct, different things. No, they are very intimately connected, intertwined, interconnected, interrelated, and so forth. Electromagnetism is just the expression of that. You cannot think very fundamentally of electricity and of magnetism in a separate way. You can't. And the mathematical transformation, the mathematical incarnation of Faraday's work and of earlier work on electromagnetism by this very talented Scottish mathematical physicist, James Clerk Maxwell, leads us to the Maxwell field equation. Again, we should stress the word field here, because that's the key word of electromagnetism, I think. And then, of course, you have the whole concept of electromagnetic field, and one of the most beautiful consequences, the concept of electromagnetic wave. And the further consequence, the unification of optics, things which have to do with light, again, and electromagnetism. Because as we will see, as you know most probably, light is an electromagnetic wave, ultimately speaking. It's an electromagnetic wave. And what that is, we will try to say quite shortly, right? So, now, this is old stuff you all know about. It's the origin of, observations, the oldest, probably some of the oldest observations on static electricity, which go back to at least 2,000 years ago, or something like that, even more. And we speak about a Greek thinker, a philosopher, a mathematician, and so forth. His name was Thalid. Okay? You know most probably in mathematics his theorem, which has to do with bundles of straight lines and so forth, right? Intersected by parallel lines. In philosophy, his intuition that everything in nature is ultimately related to water. He thought water was the origin of everything you see through various processes and so forth. But he also noticed the electrostatic attraction phenomenon that happens when you rub, like rubbing tissue or something. A piece of amber, in particular, amber, you know, amber, right? That piece of amber acquires, to use our modern terminology and language, an electric charge. And if you have little pieces of straw underneath, or powder of some kind, dust of some kind underneath, you see that the little pieces of straw or paper or whatever it is are attracted mysteriously towards this amber, right? That means amber is inducing a polarization of these small pieces of dust, and they undergo, of course, the action of the electric force, and so forth, and so forth. Anyway, this is the first. In daily life, you know, I guess, a huge amount of electrostatic phenomena, right? I have 3 children, right? The smallest one is 2.5 years old, and it happens that you have to go to the playing garden, right? And when the child goes down, shiva, how do you say that in English? That's rather non-physical. Anyway, when the child goes down this plastic object, and when I take in my arms again the small child, I get a small electric discharge. It's the same sort of phenomenon, and so forth. When you comb your hair with a plastic comb, right, your hair gets attracted quite easily, and so forth. Lots of elements of studies, of course, on these phenomena have been done since, and the main and rather fundamental observations by rubbing, okay, in a given sense, different type of objects, is that you generate different, at least, well, not at least, but you generate 2 types of electricity. Nowadays we call it positively charged, well, positive electricity if you want, if you like, and negative electricity. It's just to give it a name, huh? And the usual property which you all know of is that 2 equally charged objects always seem to repel each other. There is electrostatic repulsion, right? 2 opposite charges, or 2 oppositely charged objects attract each other, right? So this is rather known. But here we have then, you see, yes, the same Thales, wandering Greek philosopher, knew about the existence of magnetite, I mean, natural magnetic rocks, and their particular type of attraction. It attracts metals, small elements of metals especially, right? And there is this funny, you know, interaction between different magnets. I have mentioned there one name, Petrus Peregrinus de Maricourt. It's a French, there's an I, spelling mistake there. There's a French thinker of the 13th century who wrote nice little things about magnetism. He knew about the compass, right? The magnetized needle which orients itself in the magnetic field of the Earth, right? So that's another interesting question, of course. And it seems he already used iron powder dust to see what happens to them around a magnet, anticipating Faraday's techniques, you see, to visualize the magnetic field lines and so forth. And, well, these are all stories which you know, but they are quite important because also for magnetism, it seems you have 2 types of magnetic poles. Like, electricity, for electricity you have two types of charges. For magnetism you have two types of magnetisms, if you want. And the two types are called North Pole and South Pole, magnetically speaking. And let us have a quick look at this small comparison, if you don't mind, between, yes, what properties a particle can have, right? If you say that a particle, a material particle, can have an electric charge, that means you're saying that that object of nature can have these two properties. Which properties? Well, mass, of course. Particles in physics have a property which we call mass. That's already quite an interesting property, really, mass. And now we are saying it is possible that the same material object which already possesses mass also possesses